right, so chapter 15, data analysis and reporting. I apologize if there's some background noise, but I've been cooped up all day and I am trying to enjoy the nice cool weather we've had for a change. Okay, so we're at the point where we need to start thinking about the data that we've collected, or I guess we could also consider it in terms of as we're preparing to collect our data, but just some things that you want to keep in mind when you are working with data or preparing to work with data. So data management. So this has to do with basically kind of your data hygiene, or um, how well you're organizing your data to facilitate analysis and interpretation and that sort of thing. So, we can look at a couple things here. So coding. So coding usually comes into play because we are working with some type of statistical software, and the software wants to work with numbers rather than strings, and strings would just be like your word combination of letters and that sort of thing. um, so um, if you use SPSS, you have a data view and you have a variable view. In the variable view, you would go ahead and set up your coding, and basically you're just assigning a number to represent um, a particular category or instance, or something along those lines. So here they use the coding for yes and no. Um, so you set it up in the variable view, 1 equals yes, 2 equals no. So as you go through and when you produce your data results, um, it'll know that it's going to report these values. Now again, in SPSS, and I'm sure the other softwares are similar, there's kind of um, a legend column where you would designate, okay, well, 1 equals yes, 2 equals no. In case of SPSS, it can work with that and it can report yes or no in your data results. But this is simply just a numerical representation of the data. Now you can use this for nominal data. So in this case, yes or no, they have no numerical value, but we can assign them these numbers. It can also work in terms of ordinal. Here's where the numbers do have, they take on more of a value, or they take on a rank order value opposed to nominal data. For example, if you had freshman, sophomore, junior, and senior, so depending on who took your survey, they indicate they're a junior. We may use 1, 2, 3, and 4. Now this would be ordinal because as the numbers increase 1 to 2, we know that their status in school increases. However, what's the problem is we don't know the numerical difference between a freshman and sophomore beyond just these numerical labels that we've placed on them. In other instances, your coding can take on an interval characteristic. So in the case of Likert response scale, strongly disagree to strongly agree. And maybe I mentioned this in an earlier lecture, but there's a controversy. I don't want to say controversy. There's a differing of opinions. Pure statisticians don't like to consider Likert scales as interval data or continuous data. They choose to keep it as ordinal, whereas within the social science, it's pretty acceptable to use Likert scale data as continuous or interval data. So if you added up everybody's Likert response on a particular item, then you could add those up and you could divide by the number of items and calculate an average or a mean. So sometimes you see that come into play, but that's all what coding is. You're just preparing your data for analysis in the way that the software wants it. Now cleaning, here's where you basically you want to check for any data entry errors. Typically, I will run a frequency analysis on individual rows of data or columns of data. And so in this case, if I'm using true and false and there should be ones and twos, then I'll get a count of how many ones there are, how many twos there are. But if there's additional numbers, I'll also get counts of those. These could be letters, just a stray, tap on the keyboard, or it could be, there may be some 11s or some 22s. Maybe I hit the number twice. But basically, you're just looking to see that, okay, the expected values according to the codes are there, and there's nothing there that's unexpected. Okay, data analysis, some terminology. Variables. Variables are just data holders. As you put together your objective statements, the intention is that they're measurable. And the way that we measure them is by assigning the data to the variables that make up the objective statement. So there's going to be independent variables and dependent variables. So what are those? Well, your dependent variables, that's what's important to you. You're interested in that particular outcome. And you want to look to see, well, what independent variables, what variables change and produce a change in your dependent variable. Right? So if we look at the examples here for gender, right? So maybe our dependent variable is attitude, some attitude score, and our independent variable is gender. What we're looking at is if we manipulate gender, right, if we switch back from males and females, is there a change in our dependent variable or attitude score? Okay, so continue on with some terminology. So descriptive statistics, sometimes you've seen that thrown around. Basically, we're just trying to characterize our data. So usually we run descriptives on the demographics of the sample, right? We're trying to describe the characteristics of the sample. How many males, how many females. Maybe we measure annual income. Okay, well, what's the average annual income? What's the range? Ages, things like that. Inferential statistics, here's where we're running our analyses, and we want to be able to make inferences or interpretations of the results. So, if you're running, non-parametric stats, you're getting statistics basically based on the frequencies or the number of responses for each category. Well, I can certainly, interpret those results, but not to the extent that I would be able to interpret meaning from results from, say, a regression analysis. So that's another thing you want to consider. 3 types of statistical analyses, and it all depends on the number of variables that you're working with. So a univariate, right? You only have one variable. So really, this is going to be your descriptive statistics. You're just basically reporting frequencies of that one variable. A bivariate analysis, okay, now we have an independent variable, dependent variable situation. And then multivariates where we have more than 2 variables. Now, this last bullet, not all analytical techniques can be used with all levels of measurement. This is true. So that's something hopefully you'll see in a statistics course as you start to run through, and maybe some of these pieces work together. But for now, just this basic understanding of univariate, bivariate, multivariate is enough to kind of get us where we need to be in terms of understanding evaluation at this point. Okay, so we've talked about this before, parametric versus non-parametric. When we introduced it the first time, we talked about the appropriate data type. So for parametric, we're talking about interval and ratio data, non-parametric, nominal and ordinal. The other thing we need to consider is the distribution of the particular variable that we're interested in. So parametric tests, we're working with a normal distribution curve. Sometimes you may have heard it referred to as a bell-shaped curve. Now, in some cases, that's not always possible, um, or so say I used this example before. So maybe you have categories freshman, sophomore, junior, senior, and you tend to have a high number of freshmen and sophomores, a relatively low number of juniors and seniors. So that wouldn't be a normal distribution of class status or class standing in the sample population. So you may want to look at non-parametric tests. So if there was a normal distribution and the data was the appropriate, your dependent variable was interval or ratio data, right? You could look at an ANOVA. A non-parametric equivalent that you would use on that non-normal distribution of class standing would be something, forgive me, I'm not a non-parametric test, maybe a Kruskal-Wallis test would probably be something that you would consider. But again, your data types, how your sample variables are distributed in the population, all of this goes into your selection of the appropriate type of analyses. Okay, here's a box from the book. So univariate, bivariate, multivariate. That speaks to the number of variables that you are analyzing. Univariate would just be one. So if we look at here, what was the average score on the cholesterol knowledge test, right? That's your only variable, knowledge, right? So you report basically a frequency, or in this case, you're looking for a mean score. How many participants at the worksite attend the healthy lifestyle presentation? Again, it's just you use the roster, roll call. You're just calculating the frequency. What percentage of the participants in the corporate fitness program met their target goal? You have X number met the goal, X number didn't, right? Again, it's just going to be a count or frequency. Bivariate analysis, now you have two variables, and you're looking at how they differ from one another. So if we look at the example, is there a difference in smoking behavior between individuals in the experimental and control groups after the healthy lifestyle program? So now you're seeing, is there a statistically significant difference in smoking behavior? And your independent variable would be either they're in the experimental group or they're in the control group, and you're just looking to see if there's a difference in behavior across those groups. Is peer education or classroom instruction more effective in increasing knowledge? So again, your independent variable would be education or classroom instruction, and you're looking at again the knowledge score. In that case, probably a t-test is what you're looking at. Do students' attitudes about bicycle helmets differ in rural and urban, right? So the setting is your independent variable, your attitude is your dependent variable. Multivariate analysis. There are some cases where you have multiple dependent variables that you want to look at simultaneously. So can the risk of heart disease be predicted by smoking, exercise, diet, and heredity? Whenever you see the term predicted, that's probably going to imply that you're using a regression analysis. So you would your dependent variable would be the risk of heart disease, and your independent variables you would enter in smoking, exercise, diet, and heredity. However, those variables were measured as a group of independent variables, and you're looking to see how they interact with one another to come up with a prediction equation, the regression analysis, to see if how those variables change. What does that do in terms of risk of heart disease? And you can read through the other examples that are similar. Okay, univariate data analysis. I mentioned this examines one variable at a time. You can do counts, basically count how many are present or absent. Measures of central tendency, so mean, median, mode. So you're looking at your average. You're looking at the middle value, where there's the same number lower than that value, the same number is higher. Mode, you're looking at the most frequent score in this particular sample. Really, again, provides a lot of descriptive so that you get a sense of the characteristics within your sample, and you can compare it with other samples to see if the characteristics are similar. In that case, then it may be prudent to compare two groups. But if the characteristics are really different, then that may be a problem if you're trying to compare it with another group, because those differences could be confounding or contributing to the change in the dependent variable. Measures of spread or variation, so that's where you're looking at standard deviation. So the way you want to look at standard deviation, so say you were shooting arrows at a bullseye target. Say you shot 10 arrows, right? A small standard deviation would be all the arrows would be tightly grouped in one area on the target. A large standard deviation, they would be spread out across the target. So again, these things tell you something about your data that you've collected in terms of again, is this what you kind of expect, or how the that particular variable, how it's distributed in across the sample. Okay, bivariate analysis, again, two variables. Used for hypotheses testing. So if you're not familiar with hypotheses testing, it's typically based on this idea of a null hypothesis. So null means absent. So if you had individuals in an education group versus a classroom group, and you're interested in knowing, does one group perform better on a knowledge test than another, the way that you would write out your null hypotheses would be that you would say there is no difference between the groups in terms of knowledge score. And so then based on that null hypothesis, you set up your hypotheses testing. And the way that it works kind of in a general sense is that there's two possibilities. Either you reject the null or you fail to reject the null. And it's all based on statistically significant evidence to either reject or fail to reject. Now, fail to reject means that you didn't find enough evidence to say that there is a difference between the education group and the classroom group. Notice I didn't say accept the null. I know sometimes you'll come across literature that they say accept the null. I don't like to use that kind of terminology. I'd rather stick with fail to reject, simply because that means that, hey, I haven't collected enough evidence for me to reject it, so I fail to reject it. Lack of evidence doesn't prove anything, so that's why my preference is not to use accept the null, but rather state it as fail to reject. Your alternative hypotheses, alternative to the null. So if the null is that there is no difference between the groups, the alternative would be there are differences. So if you reject the null, right, then you go with the alternative. Statistical significance. Really, this is what it comes down to. So you may be comparing the means between two groups, and numerically you're looking at them and you say, hey, yeah, these are different numbers, they must be different. But statistical significance is a probability that you're not committing a type 1 error, and we'll address that here in a minute. And there's a 95% chance, because typically we use p is less than or equal to 0.05 as our significance level. However, you can have a more stringent significance level depending on what's common in that particular discipline or that particular type of study. All right, so here's the type 1 error I was talking about. Failing to reject when the null hypothesis is true. That's possible, and that's with it when you have, if we go to significance level down here, less than 0.01, you're saying that there's a 99% chance that you're not making a type 1 error. On the other hand, a type 2 error, failing to reject when the null hypothesis is not true. Okay, so there's a chance you're going to make one or the other error, and the significance level through calculations and that the data run through kind of minimize that. Or if you cross over those thresholds of 0.01, 0.05, then you have some level of confidence that what your analyses has detected is actually what's going on. Typical analyses that you see, depending on your data type now, right? So bivariate analysis, we have two variables that we're interested in. The dependent variable is nominal. Your independent variable is nominal, or ordinal, or a combination of the two. Then you would use a chi-square, and chi-square is just based off of frequencies or counts within each variable category. If you have interval ratio data, then you're comparing the means among two groups. You use a t-test. If you have three or more groups, so an example of two groups would be gender, male, female, right? There's only two groups. So if you're comparing the mean score of males compared to females, you'd use a t-test. If you had an independent variable where you had freshmen, sophomore, junior, seniors, and you want to compare their test scores, then we would use an ANOVA or analysis of variance. Like the bullet says, it's a t-test for three or more groups, categorical groups. Correlations. Correlations are probably the most common analyses out there, probably one you're most familiar with, and you're just looking at when there's a change in one variable, there's a simultaneous change in either the same direction or opposite direction. It'd be a positive or negative correlation. The thing with the correlations, though, it's the correlation, the R value, is strictly based on the data you observe. So you could draw a box around your data points if you graphed it. The correlation doesn't try to do any prediction, so it doesn't extend out beyond the data that you've observed. So unlike a regression, right, if you want to predict values that you haven't observed, then a regression is what you would go to. So a correlation is a very weak statistic, and it basically just tells you that the two variables are linked in some way, but your ability to infer anything about that link is fairly limited. All right, so here's a correlation. So the green lines represent possible slopes, and the slope is reported as your R value. Right, so R value goes from 0 to 1. 1 would be this perfect 45-degree angle. Or excuse me, it would go from it would rise from left to right. That's a positive correlation. If it falls from left to right, that's a negative correlation. The strengths are the same, so if you had a negative 0.5 R value, that would have the same strength as a positive 0.5 R value in terms of the correlational relationship. It just negative simply means that as one increases, the other one decreases, or vice versa. Okay, multivariate data analysis. So now you're looking at three or more variables simultaneously. Regressions is typically where you're going to find that. Discriminant analysis, not something that I've ever used or know much about, but I'll assume that the book is correct here. But factor analysis, that's something I'm very familiar with. Factor analysis is where you would, so say you had a single questionnaire and a single scale that measured several dimensions. So say you had a questionnaire that was designed to measure the constructs of the theory of planned behavior. Ideally, if you ran that through a confirmatory factor analysis, that the questions that addressed each particular construct would group together, and it's loosely based on correlations and some other calculations, but when it works out, well, it's pretty neat. So the example that I've always been familiar with, or kind of a classical example of factor analysis, is you would take a survey that tried to assess your musical genre preferences, right? Like country, rock, jazz, easily listening, rap, whatever. And again, you run it through a factor analysis, and the questions that pertain to each genre, right, they should separate out from one another and group together. Like I said, it's pretty neat when it works out. Multiple regressions. Again, we're trying to predict that if we were to change, the independent variable by X amount, we could expect a change in the dependent variable by X amount. Different types of multiple regression. Now the book lists stepwise, and stepwise is a technique where you try to control for the effect of variables that you're not really interested in, but you recognize that they play a role in, or they influence the change in the dependent variable. And by entering the variables in different steps of the analyses, you can kind of control for their effect. Now, stepwise is not usually recommended because the computer software kind of determines what steps the variables are entered in on, and there's really no rhyme or reason pragmatically when that happens. So the alternative to stepwise is called hierarchical. Same concept, except the researcher determines at what step which variables are entered, so that they can control for confounding based on, again, what the researcher knows about the variables. A logistic regression is where you would have a nominal dependent variable, right? Yes or no. And you have interval or ratio independent variables. And basically it comes up, as the independent variables change, are they, more likely to be a yes or a no? General linear, that's typically where you have a numerical dependent variable, the interval or ratio, and logistic general linear. You're going to see them, as often as one another as not. Pretty common. I'll let you kind of go through these slides. Look at the nomenclature. Look at what your variable letters, your coding stands for, and basically you can kind of see how the variables are laid out and the treatments are laid out, and how you can go about collecting. But look at, we're looking at nominal data. The data analysis is a chi-square. That's what we would expect. And the chi-square, like I said, it's a 2x2 table, and it's simply based on frequencies, and that's where these proportions come from. What are we looking at here? We got ratio data. We did a t-test, so we're just seeing if group 1 differs from group 2 on knowledge of HIV. Okay, it's all based on mean scores, pre-test and post-test. So we're seeing if there's a statistical difference in 69 between compared to 78.5. Okay, interpreting the data. Interpretations. This is really kind of the discussion section in most manuscripts, and really that's the only one part where the researcher gets to kind of express their opinion about what's going on. Now it's an educated opinion, but it's an opinion nonetheless. So in that case, you want to make sure that there's other members on your team are also coming to the same conclusion, same interpretations. It's just a good practice. Oh, this last bullet. Well, let me go through the other one. Program significant measures are the meaningfulness of a program based on stakeholder preference, regardless of statistical significance. Significant significance determined by statistical tests. Okay, so what they're saying is there's going to be instances where you find that the results are statistically significant. However, when you look at the effect size, basically the magnitude of difference, it's relatively so low that, again, pragmatically, it really doesn't, you know, make that much of a difference. Again, you would look at something like Cohen's D as your effect size, and there are some cutoffs and rule of thumbs for utilizing Cohen D as to what would be a small, moderate, or large effect. Of course, you know you're interested in the moderate and large effects more so than not. Okay, 8 methods of interpreting data. Um, Determining whether objectives have been achieved. Okay, so that's why we set up measurable objectives so that we can evaluate them and say that. Determining whether laws, democratic ideals, regulations, or ethical principles have been violated. Again, these are just kind of in general. I'm not going to go through them. They're pretty straightforward. You can just kind of read them and see, you know, what you would consider or may want to consider as you're going through and interpreting your results. Okay, reporting your evaluation. You know, you have to think about what the results mean, and it may mean different things to different groups, or different groups may be interested in different aspects or elements of the evaluation rather than a total evaluation of the analyses. So you have to be able to speak to your audience as far as, you know, what this evaluation represents, and sometimes you may need to tell people or interpret results for people so they understand the meaning behind the results. Oops. Okay, so all this is saying is up front you should have a good sense of what your evaluation plan is going to be, and because this is going to help you stay on track as far as collecting data, analyzing it, and reporting it in a timely manner. For formative evaluation, remember this is before and during implementation. So, you know, collecting and analyzing this data gives you a chance at making corrections while the program's running, again, to maximize the potential for success. Summative evaluation, remember, that's after the program ends. So basically you're summarizing all the effects that have happened within your program. So that's going to be kind of your final report. You know, looking back on the program, you're able to reflect on the data a little bit more, and kind of tease out what the true meanings are behind some of the results that you find. You know, your stakeholders, the people that are funding your project, right? They have different interests. So your evaluation report has to meet the needs of everybody that has a vested interest in your program. So you must be able to, you know, adapt and present the results in different ways, not just to a scientific community, maybe to the layman, to someone that's not familiar with statistical analyses and what that means and what that represents, right? You're going to have to utilize what's called social math, basically break down the results into a way that's easily consumed by the particular audience that you're presenting it to. And then your written report. Basically, this follows typical manuscript format. So you have an abstract that basically, you know, gives a little bit of a snippet. So imagine you had a bunch of reports and you're sifting through them trying to find out, you know, which ones are pertinent to your interest. Right? You would look at the abstracts, and that's going to give you a very brief summary of, you know, the nature of your study, characteristics of your sample, your results, and then kind of the major findings or your interpretations. But for the rest of the paper, your introduction, your methods, basically your study design, your results after your analyses, and then the discussion includes your interpretation of results. When you're presenting the data, data presentation should be simple and straightforward. Again, most people are visual learners, so if you can use tables and graphs to help illustrate. Sometimes you maybe talk about a difference, but when you present it in terms of a bar chart, the differences just jump out at you. So again, you're going to have to select the appropriate type of graph that kind of imparts the effect that you're after. Again, people rather see things at a glance than kind of have to read through paragraphs of information. So again, and that's true for most audience. Even the scientific community can appreciate graphs just like the general population does. This just goes through the different types of graphs and charts that you can utilize. Again, you want to pick one that really helps you make or emphasize the point that you want. And again, different layouts can have different effect on the audience. Just some suggestions. Give key decision makers advanced information of the find. So kind of give them a little heads up. Here's what we found. This is kind of what I'm going to be presenting. Maintain anonymity of individuals, institutions. We do that when we write manuscripts. So if I conduct a study at FAU, I wouldn't necessarily name FAU in the write-up. I may say a public university in the southeast of the United States, something like that. Okay, so increase the utilization of results. So you go through all this trouble of evaluating, hopefully the results serve a purpose. So plan the study with stakeholders in mind. What are they after? What are they interested in? Okay, well, adjust your presentation results to meet that. If the program changes after the planning stage, right, because you're planning your strategies and the program itself, but you're also simultaneously planning your evaluation plan. So if your strategies change, well, you better start looking at your evaluation plan to see if it's still applicable. Focus the evaluation on conditions about the program that the decision makers can change. Again, you're going to present results to the stakeholder and say, hey, look, these were the results. If you want to increase or decrease, then you need to make some decisions in these areas, right? You don't want to give them results and saying, hey, here's what the results were. There's nothing you can do about it if going forward. What's the utility of that? Reports should be written in a clear, simple manner. Right? Nobody likes to read through a bunch of scientific jargon to kind of get to, just tell me what's the important stuff. Let me know what that is. Decision on making recommendations should be based on how clear the data are. So, if you're going to be making evidence-based decisions, then you want to make sure that the evidence clearly supports, a decision one way or the other. Disseminate the results to all stakeholders using a variety of methods. So disseminate means, okay, so you got these findings. How are you going to inform all the stakeholders, right? Are you going to write this up? Are you going to do a presentation, PowerPoint? Are you going to make a video? Basically, how are you going to share the findings with everyone? Integrate the evaluation findings with other research and evaluation about the program. Sure, you may be focused on one particular aspect, maybe behavior change, but there are maybe other elements of the program that groups are evaluating that, hey, maybe we can have a comprehensive overview of the evaluation and provide high quality research, right? That's goes without saying.